Okay, this video is about how to find a Taylor polynomial. We have two learning objectives. The first one is a mouthful, but really the first one is what the primary focus of the video is. Be able to generate a Taylor polynomial. So to do that, I'm going to be demonstrating or providing for you a formula in this video, so you'll need to know the formula and be able to apply it. We're going to do the formula for a Taylor polynomial centered at C, where C stands for center, but we're also going to talk about how to apply the formula to something called a Maclaurin polynomial. Hopefully, from the last video, you already know what a Taylor polynomial is and what it's used for. So in this video, we'll just talk about how to generate that. And then the other thing we'll do is we'll discuss some of the vocabulary associated with Taylor polynomials. Like, for example, what is a Maclaurin polynomial? What does it mean to have the nth order polynomial? Those sorts of things. So that's the focus of this video. To get to the formula, what I'd like to do is just remind you of the process that we did in the last video. Okay, so I'm not going to go through all the details of this because it's already in the last video. I just want to remind you, hit some of the highlights of what we did. So first of all, the goal in the last video was we tried to generate a polynomial that would represent the e to the x function centered at the origin. Okay, now some of the other vocabulary that's up here, we'll develop that over the course of this video, so don't worry about that too much. Just going from your memory of the last video, this is what we were doing. We were generating a polynomial that would mimic this function when we were close to the origin. And so we identified, first of all, how many terms there were going to be. Okay, that was the first thing we did. And we said in order to find the polynomial that behaves correctly, we're going to have to carefully figure out what those four coefficients are equal to. And then we went through this process. And one of the things that hopefully you started to recognize as the video went on is that the process proceeded in a very predictable way. The first thing we needed was we needed the value of the polynomial to equal the value of the function. So we set these two things equal to each other. We plugged 0 into both of them. So here I've got my work for plugging 0 into the polynomial. Here I've got my work for plugging 0 into the function. And then we took those two answers. We set those answers equal to one another, and that enabled us to get the first term of the polynomial. Okay, now my goal in this is to make sure we recognize that there's a consistent pattern. So then the next thing that we needed to do was zoom out a little. There we go. The next thing we needed to do was to figure out a value for the next coefficient so that the slopes would be the same. And so when we wanted the value of the functions to be equal, we set the two functions equal. Now we want the slopes to be equal, so we set the two first derivatives equal. And then we go through the exact same process. Figure out what the first derivative of the polynomial is going to be. Figure out what the first derivative of the function is going to be. Set those two things equal to each other, and that enables us to figure out the next coefficient. Then we did it for the second derivative. The second derivative allowed us to ensure we had the same concavity. So we set the two second derivatives equal. We figure out what the second derivative of the polynomial is. We figure out what the second derivative of the function is. We set those two things equal. That enabled us to find the next coefficient. Okay, so this was the consistent pattern that we saw. And same thing on the third derivative. Set the two derivatives equal, figure out what the first derivative is, figure out what the other derivative is, and that enables us to establish an equation that we can solve to find the next coefficient. Now, we also discovered that there were some predictable pieces to this. Like, for example, we talked about that when we set the derivative of the polynomial, or I shouldn't say set, when we plug 0 into the derivative of the polynomial, we're always going to end up with the coefficient that we're looking for with some multiplied thing in front of it. And the thing that's in front of it was always coming from the fact that I had to take the previous exponent's factorial. Because every time I took a derivative, let's just focus on this real quick. Here I'm not taking any derivatives, so nothing happens. Here I took the first derivative, so when I take the derivative of x, I just get a 1, which is the same as 1 factorial. Here I took the second derivative, so when I took the first derivative, I got a 2. When I took the second derivative, I got a 1. 1 times 2 is 2 factorial. Here I'm taking the third derivative, so when I took the first derivative, I got a 2. When I took the second derivative, when I took the first derivative, I got a 3. Second derivative gave me a 2. The third derivative gave me a 1. That's equal to 3 factorial. And so what I have in every one of these situations is that the number in the bottom of my fraction, I could think of this as being a 1 over 1. I could think of this as being a 1 over 0 factorial. The number in the bottom of my fraction is the exponent of that term factorial. And so you can see, because there's this consistent pattern, that's going to generate a piece of the formula. In fact, let's just talk about this right now. A single term has 3 parts. And we can see this in all of these terms. One part is the denominator to the fraction. And what we've just established is the denominator is going to be whatever the term was. So the constant term, the linear term, this quadratic term, the cubic term, whatever that exponent is for that term, factorial. So I'm just going to call this the nth term. So if n is equal to 0, then I've got the constant term 0 factorial, because this would be x to the 0. If n is equal to 1, then I've got the linear term. N represents the exponent. So n equals 1 is the linear term. I've got x to the first. N equals 2 would be the quadratic term. N equals 3 would be the cubic term. And so what we're finding is the number in the bottom of this fraction is simply n factorial. Okay? Now, I said there's 3 parts to every term. One part is the bottom of the fraction. The other part is the variable part. And that's fairly straightforward. It's just simply x to whatever exponent, and we're defining the exponent as being n. So that part's nice and easy. All that leaves then is the top of the fraction. Now the top of the fraction, at first, it looks like it should just be ones, right? But let's talk about where those ones come from, because it's not always straight ones. With this particular function it is, but it's not always. So let's think about where the top of that fraction came from. Here's the top of the fraction. Let's trace it backwards. The top of the fraction was what we substituted into this equation, and what we substituted in was the value of a derivative at 0. So in the case of the e to the x function, no matter how many derivatives we take, when we plug in 0, we always get 1. That's why the tops of all of these fractions were 1s. But if we had a different function, they wouldn't always be 1s. And so what we want to say is that it's not necessarily always a 1, but what it is always is it's the derivative of this function evaluated at 0. Now, the next piece of notation is advancing some notation that we've already seen. So before I write this down here, I want to remind you of something that we've talked about before. Remember, with Newton's method of representing a derivative, he took Euler's function notation, and then initially he started just putting tick marks next to it. First derivative, second derivative, third derivative. But do you remember what Newton did after the third derivative? He didn't just keep putting tick marks, because that would just eventually start making lots of tick marks. What he did was he would put the number of the derivative that you were on, but then to make it clear that this is not an exponent, it's a derivative, he would put that number in parentheses. So the way we would represent the nth derivative is we would say, there's my function. I'd put an n up here, but so that it doesn't look like the n power, so that we know it's the nth derivative, we would put that in parentheses. Okay? So If it's a 1, then I end up with the first derivative. If it's a 2, I end up with the second derivative. So this would be the same as this. And this second derivative would be the same as putting a 2 in parentheses. If we follow this pattern backwards, then what we would say is if I was at the 0th derivative, that's the same as the actual function itself. And that's the notation that we'll utilize when we're generating these types of polynomials. So this notation means take the derivative, the nth derivative. If n is equal to 0, then you're just doing the function with no derivatives. If n equals 1, then it's the first derivative, n equals 2 is the second derivative, so on and so forth. Okay, so this becomes basically a formula for finding a single term. And then what do we need to do? We need to add all of those terms together, because that's what polynomials do. They add terms together. We're going to add all of those terms together. So, mathematically speaking, oops, this is for a different class. Here we go. Mathematically speaking, how do we represent that we're adding a bunch of stuff together? We would say, find the sum as we go from 0 to however many terms we want, the nth term. And then we've got our formula. We said that the bottom of the fraction would be whichever term you're on, factorial. The top of the fraction would be the derivative evaluated at 0. And then you would have an x raised to the power of whichever term you're on. So this becomes our formula. Okay? Now, we need to introduce a little bit more vocabulary at this point. It's the formula for what exactly? Well, the way I've got it written here, this would be the formula for a Maclaurin polynomial of order n. So the Maclaurin polynomial of order n. So what we would say, we've got a polynomial of x, and then to show that it's of order n, we'd put a sub n. Okay, so this is our first formula. This is our first formula. This is the formula for a Maclaurin polynomial of order n. Now, at this point, we can't kick this can down the road any further. We have to talk about what these two words or phrases mean. What does it mean to be Maclaurin? What does it mean to be order n? Okay, so order n simply refers to what's the biggest number you plug into this sigma notation. Okay, order n, aka the nth order, what that tells you is the upper limit on your sigma notation. Okay, so that's how many times you're going to go through this process. You're going to start at 0 and you're going to go through this. So you're going to go through this n plus 1 times. If n was equal to 3, like on the example that we just did, n was equal to 3, so we had to go through this four times altogether. Okay, so basically n is telling you how many times you're going to have to go through this process. That's what the n refers to. Now, the Maclaurin part, what that does is it tells us where the center is. And where was the center on the problem we just did? The center was at 0. So a Maclaurin polynomial is a Taylor polynomial whose center is at x equals 0. Okay, a Taylor polynomial can have a center any place. A Taylor polynomial, the center can be any place, but with a Maclaurin polynomial, the center is only at 0. It can't be anywhere else. So if you remember in the last video that we did, I mentioned that the Maclaurin polynomial is actually the easier version of the Taylor polynomial. And the reason why it's easier is because it's always easier to do something at 0 than it is at some other location. Okay? So Taylor polynomial, it can be centered anywhere. A Maclaurin polynomial is centered at 0. Okay, so what would that make our equation for a Taylor polynomial? Let's go ahead and write this. And this, I suppose, is probably our more important equation. Okay, so a Taylor polynomial of order n centered at x equals c. Okay, I guess we could say for the function f of x. And really that's what we've got here too, right? That's what we've got there too. Okay. The reason why I know it's function f of x is because I'm using an f in my formula. So remember from the last video, what a Taylor polynomial, and so therefore also a Maclaurin polynomial, what they're doing is they're giving you a polynomial that enables you to approximate the value of a function as long as you're close to the center. And the larger this number is, the further away from the center you can be and still get pretty decent approximations. That's what we talked about in the last video. So here's our formula for a Taylor polynomial. Same beginning part, the polynomial of order n will be equal to, because it's a polynomial, we're still finding a sum. We're still going to start with a constant term where the exponent is going to equal 0. And we're going to still do this a total of n plus 1 times, so we're going to go from 0 to n. Now what changes though, I still have to take derivatives. I still will have to divide by factorials because that chain rule, or not chain rule, but power rule happening over and over and over and over again. The difference is now I'm not going to find the value of the slope at 0 anymore. I'm going to find the value of the slope and the function, the concavity and everything else at the center. So that's the first difference, is in a Maclaurin polynomial, I'm finding the value at 0, but in a Taylor polynomial, I'm finding the value at some other spot. It could be 0, right, because Maclaurin is just a special case. So it could be 0, but it could be anywhere. The next piece is the x part. So remember when we learned in advanced algebra and then again in pre-calc, if you take a graph and you just shift the center of the graph to the right or to the left. So here we're centered at 0. Here I'm just shifting my center to a different spot, maybe not necessarily 0. The way we represent that in the equation is just simply by adding or subtracting a number from x. And so what happens is if we are moving, let's say we move c units to the left, then I would end up with an x plus c. If I move c units to the right, I'd end up with an x minus c. So if we allow c to be both a positive number, meaning we're moving right, or a negative number, meaning we're moving left, then just simply using this expression will always work. And so this becomes our formula for a Taylor polynomial. And this then becomes the first half of objective number 1, know the formula. So there's our formula. Okay, there's objective number 1, know the formula. Now the second objective was to apply the formula, and we will do a little bit of that in this video, but honestly that's going to be the focus of the last video in this unit, where we're just going to work through some examples. Okay, before we get into examples, actually, you know what, as far as examples go, the first example that we walked through that we reviewed from the previous video, that's going to be as much of an example as we do in this video. I'll save the examples for the next video. So the only other thing we need to do is we need to talk about some details as far as vocabulary goes. So we've got basically this becomes more or less our definition of a Taylor polynomial. If you look at the definition in your textbook, it's this. They just give you some specific details about the fact that n has to be an integer and et cetera, et cetera, et cetera. But this is basically our definition. From the previous video, we understand that definition to imply that the purpose of a polynomial is to approximate the value of a function. Okay, so we know the definition now, we know the purpose. We also know the difference between a Taylor and a Maclaurin. We know that. And we know what the phrase order n means. Now here's the last bit of vocabulary that you have to be a little bit careful of. Remember when we studied polynomials back in algebra class, we learned to talk about polynomials based on two different characteristics. The first characteristic was the number of terms. And the second characteristic was the largest exponent. Okay? The number of terms and the largest exponent. We talked about polynomials based on those two things. Now, what I'd like to do right now is to first of all reassure you of the fact that those two concepts haven't changed. Okay, so just because we're in calculus class and we're talking about a special kind of polynomial, what you learned about these two concepts has not changed. But what I want to do is tie these two concepts to the idea of an order, because they're not exactly the same. And if you get them confused or mixed together in your mind, then you've got to be a little bit careful. Okay, so of order n, what we know is that gives us an upper limit to the number of terms we could have. This is kind of written up. I'm going to look at this one here where it's just a little neater, even though that we haven't figured out what this was equal to yet. We know it's equal to 1 over 6. Okay, so it's a little bit neater here. So let's take a look at this. This was a Taylor polynomial of order 3 because we went to the third exponent. Okay, this was a Taylor polynomial of order 3. And so what we found was none of these terms were equal to 0. So how many terms did we end up with? We ended up with 4 terms altogether. Okay? So the number of terms will never be more than the order plus 1. So this was an order 3 polynomial, and we ended up with 4 terms. We would never have an order 3 polynomial. There's no way I could have another term after this, right? Because if there was a term before it, if we went to x to the 4th, then that means we did the sum from 0 to 4. And so now that's a 4th order. If we go 0 to 3, then that gives us a 3rd order. And there's no way that we could have something after the constant, or it's not a polynomial anymore, right? If we add in something like this, that's no longer a polynomial. Now that's a rational, right? So that's something different. So what we find is the connection between the order and the number of terms is at most the number of terms will be the order plus 1. Okay, now at most. Now why do I say at most? Why do I say at most? The reason I say at most is because it's very possible, and we will see this in the next video, that some of these coefficients could equal 0, right? So let's just say for the sake of argument that I did this problem and I got a 0 for this coefficient. So now there's no x's and then it's just plus 1. So this only has 3 terms, 1, 2, 3, but it's still an order of 3. So the number of terms ended up not being the order plus 1, it ended up just being the order. So that's why it's at most, because it certainly is possible that some of your coefficients could equal 0. Okay? Now, the same thing happens over here. The largest exponent, which we know the word for the largest exponent is the degree of the polynomial. The degree of the polynomial will at most be equal to the order. Equal to the order. Okay? So thinking again about this example that we just looked at, we talked about this exponent could never be bigger than the order, because order 3, if I had in order 4, if I had an exponent of 4, then that means I went up to 4 in this equation, so that was a 4th order. So it can never be bigger than the order. So 3 is the biggest it could be. But again, sometimes these coefficients are equal to 0. Suppose, just for the sake of argument, that I did this process on some function where a sub 3 was equal to 0. Okay, so when we did it, we got 1/6, but suppose that that's what we ended up with. So now what I have is there's no term here. I'm missing the x term. I end up with something that just looks like this. And so even though it's a 3rd order, it's only a 2nd degree polynomial. Okay, so remember, the degree and the number of terms is not exactly the same as order, but all 3 of them are connected to each other because they create boundaries. The order of the polynomial creates a boundary for how many terms you could possibly have. You'll never have more than the order plus 1. And it also creates a boundary or an upper limit for the degree. You'll never have a degree that's bigger than the order. Okay? You could have a degree that's less, but you'll never have one that's bigger. Okay, so that takes us to the end of this video. As I said, in the next video, we will be looking at examples. And so the more of the how to apply part, we'll be fleshing that out more thoroughly in the next video. In this video, we applied it a little bit, borrowing from our last video. Now we know what it is. And we also now have seen the vocabulary that's associated with this polynomial. So that takes care of this particular one. As I always say, let me know if you've got any questions. In the next video, we'll do some examples. Thanks for watching.